Welcome to this explainer. Today we're diving into a journey that literally every single programmer goes through. It's that frustrating, but honestly kind of magical leap from writing basic, messy scripts that merely function to designing truly brilliant optimized Python code. We've got some fantastic recent insights to break down exactly how you can level up your programming game right now.
So, here's a crucial, foundational question for anyone who spends their days staring at a code editor. What is the actual difference between code that just works and code that is truly brilliant? I mean, you can usually force a script to finish a task, but the gap between functioning code and brilliant code, that's bridged by three vital things: problem solving, optimization, and error handling. Today, we're going to discover how mastering these specific areas can totally transform your applications from sluggish scripts into, well, elegant software.
Okay, let's dive right into this with Section 1, Decomposing Python Problems.
You know, problem decomposition is really just about breaking down a massive, intimidating challenge into bite-sized, solvable pieces. Let's take a seemingly simple challenge, generating 10 random numbers between 1 and 100 on a single line. When you just hear the prompt, it can feel completely overwhelming. Where do you even start? But if we decompose it, it becomes three really distinct, manageable milestones. Step 1, you just isolate a single random number using Python's built-in random module. Step 2, run a standard for loop 10 times to grab our batch of numbers. And Step 3, format that output with spaces so it prints neatly on one single line. Sure, it's a slightly naive approach, but by breaking the prompt down, we get a working solution incredibly fast.
Which brings us nicely to Section 2, Supercharging Math with NumPy.
Getting your code to run is awesome, absolutely. But we don't just want working code, we want brilliant code. So the question you should be asking yourself the very second you get a script to successfully execute is, how do we make this run faster? Our standard loop works totally fine for 10 numbers, but what if we needed 1,000,000? Well, Python has some incredibly powerful external libraries that are specifically designed for high-speed, complex numerical operations. The contrast between the two approaches is night and day. On one hand, we have the verbose standard loop. It kind of acts like a slow turtle, needing multiple lines of logic just to get our numbers out. On the other hand, we have the rocket ship, the single-line elegance of NumPy. By using the np.random.randint function, we declare our start point, our end point, and our exact sample size all in one go. Why is this such a game changer? Because while NumPy's front end is written in Python, its back end is actually running on the much faster, low-level C language. It performs the exact same task exponentially faster than a pure Python loop ever could.
All right, let's move on to Section 3, the Planet Weight Calculator.
Let's look at a highly practical project to see how we handle real-world data constraints. Imagine a program where a user inputs their Earth weight to see exactly what they'd weigh if they suddenly teleported to other planets. This beautifully illustrates the concept of data mapping. We have specific gravitational constants for our solar system. For Earth, the baseline is 1.0. Mars is 0.378, and if you somehow head over to Jupiter, you're looking at a whopping 2.36 times your Earth weight. By mapping these constants to a dictionary in Python, we just multiply the user's Earth weight by the specific planetary constant, and boom, we instantly get the exact weight for any planet.
But there is a bit of a catch. When we multiply these float values, we often end up with these messy, infinite, decimal-heavy numbers that look absolutely terrible to an end user. I mean, nobody wants to know they weigh exactly 65.33333 kilos on Mars. So the crucial step here is refining our output. By using Python's built-in round function and passing 2 as the second argument, we force our mathematical output to a really neat 2 decimal places. It's a tiny, simple tweak for sure, but it makes the application instantly feel far more professional and user-friendly.
Now for Section 4, Optimizing Code and Memory. So now that our weight calculator is beautifully formatting the numbers, we hit a structural roadblock when it comes to optimization. If we define our dictionary of planetary constants inside our calculation function, it's getting redundantly recreated from scratch every single time the function runs. Think about the memory lifecycle here. When a function is called, memory gets allocated. When it ends, Python's automatic garbage collector has to sweep in like this overworked janitor to free up that space. If you have 1,000 users, you are literally building and destroying that heavy dictionary 1,000 times. Instead, if we pull that constant data outside the function as a global variable, we create a cache. We save the garbage collector from constantly having to clean up after us, which makes our code dramatically lighter and way faster.
Moving right along to Section 5, Bulletproofing with Try-Except. Because let's be honest, efficiency is amazing, but stability is just as important. What happens when a user is asked for their weight, and instead of typing 50, they accidentally hit the keyboard and type the letters 5T?
Without safeguards in place, the entire script is just going to crash immediately. Python throws what's called a value error. This basically means the operation received an argument with the right overall type, but a completely inappropriate value, kind of like trying to do long division on a letter. Brilliant code doesn't just crash and burn, it anticipates and intercepts these known user errors before they have the chance to bring down the whole application.
The source material shares a highly relatable bank transfer analogy to explain this concept perfectly. Imagine you have $100 in your bank account, but you try to send someone $150. The system stepping in and stopping you? That is an expected error. It's a completely predictable point of failure. In the exact same way, we know for a fact that users will sometimes accidentally type letters instead of numbers. We should entirely expect it.
And we handle that expectation by catching the errors using a try-except block. Think of it as a safety net for our code. Wrapping our risky input code inside a try block means that if a value error does pop up, Python just skips the fatal crash and immediately triggers our except block instead. We can use that block to gracefully intercept the mistake, tell the user, hey, please enter a valid numeric weight, and safely prompt them to try again, without ever breaking the core loop.
And finally, Section 6, Building the High-Low Game.
Now it is time to tie the whole shebang together. We're taking random number generation, memory management, and robust error handling and using them to build a multi-round high-low number game. The mechanics are simple. At the start of a round, the computer generates a secret number for itself and assigns a random number to the user. Then the computer asks the user, do you think your number is higher or lower than my secret number? The user makes their choice, the truth is revealed, and if the user guesses right, we track that score on a leaderboard.
Now, building a whole game sounds incredibly complex, right? But the core logic statement is actually remarkably simple. If the user chooses high, and the user's number is actually greater than the computer's number, well, it equals a win. It really is that straightforward. Great software isn't magic. It is quite literally just a series of small, solvable logic checks layered on top of one another. We take the user's input, check it against our rules, and handle the outcome.
By breaking down massive problems into small milestones, leaning on powerful libraries like NumPy, managing memory outside of your loops, and anticipating user errors with solid safety nets, you stop writing code that merely functions and start writing code that is undeniably brilliant. So the question I really want to leave you with is this. Looking at the projects you are building right now, how will you optimize your own code tomorrow? Thank you so much for joining me for this explainer, and happy coding.